Hello. So in this video, we are going to be talking about the process of simplifying radicals. So we're going to talk about sort of initially the process of simplifying numeric radicals, and then we'll talk about algebraic radicals. And really, the process is the same either way, but it's sort of helpful to use the number part as a starting sort of spot and then go to the algebraic part. Before we do that, though, it's sort of worth a mention here. Again, I'm sure I have said this in other videos before, and I will again. But the whole thing about radicals, right, is that you can't just distribute radicals over multiple terms. But that means that you can only really simplify radicals once the radicand itself, the part inside, is fully sort of factored, or is at least, in a factored form of some kind. So in particular, right, if the expression inside the radical is not factored, you can't simplify it. You can't do anything, right? You have to sort of go back and factor it. So if you have something like the cube root of x cubed minus 27, can't do anything with that. That is not x minus 3. That's not true, right? You have to sort of do stuff with it in order to get it into a factored form. So you would have something like this, and then once it's in a factored form, that's when you could actually calculate the root or simplify or whatever it is you're trying to do, okay? All right. So again, I know I'm just reiterating this over and over, but like this really is where everybody goes wrong, and it seems like it doesn't always get across. So trying to distribute radicals does not work. Do not do it, right? It's the most common mistake from this sort of section. If you have multiple terms, you absolutely have to factor it first, right? And this is true actually regardless of whether it's algebraic or numeric, although with numeric stuff it's sort of easy because you can just put the terms together. They're all numbers. But this is true regardless of the nature of those terms. If you have more than one term, you have to do something to get rid of that fact. You have to put them together or, factor or whatever. Once it's factored, then you can move on to simplifying. So this is always sort of step 0 for any kind of radical problem, pretty much. All right, so with that out of the way, numeric radicals. So step 1, right, with numeric radicals, the whole idea of simplifying radicals, as I keep saying, is to factor the thing. So we're going to factor even numeric radicals, and in particular, we're going to do this by factoring into its prime factors using this prime factor decomposition tree. So if you haven't seen that, I'm going to sort of demonstrate that here. So let's say we're trying to do some sort of root of 36,000. So to get the prime factors of 36,000, you basically just want to look at this and be like, I need two numbers that multiply together to get that 36,000, right? And any two numbers are fine. Looking at this, my first thought, right, with all those zeros at the end, I can make this into 36 times 1,000. Then you go to each of these numbers, and you basically do the same thing. You say, okay, is this thing prime? 36 clearly not prime, so I'm going to sort of break that apart and say, okay, what are two numbers that get 36? Any two numbers work. I will look at that and think, okay, how about 4 and 9? Then I go and do the same thing to 1,000, right? I say, okay, is 1,000 prime? Clearly not. What are two numbers that multiply to 1,000? Well, that's going to be, let's say, 10 and 100, right? So then I put those down. Rinse and repeat the whole way through. So 4, is that prime? No. Two numbers, 2 and 2, all the way through. So I'm going to get that 4, right? 2 times 2, 9, 3 times 3, 10, 5 times 2, 100, 10 times 10. But now when I look at it, I go, is 2 prime? Ah, yes, 2 is prime. 3 is prime, 5 is prime, all of these sort of things that are prime. That's when I stop with that part of the tree. And it's helpful to circle these to sort of remind yourself that you're like, okay, I've gotten to this sort of prime, now I can stop on that sort of part. And it might be that only one side of it, right, is prime. So you could have like 2 times 10 or something, and then you'd circle the 2, but you keep going with the 10. Same idea. Here, since the 10s aren't prime, I would, break those further down, but the 5 and 2 are prime, so now I'd circle those, okay? So this is how you do the prime factor tree, and what I'm looking at is, once I've gotten down to all prime numbers, right after everything's terminated, then that tells me what numbers I multiply together to get the original number. So in particular, looking at this, I can be like, okay, so 2 times 2 times 3 times 3 times 5 times 2 times 5 times 2 times 5 times 2 is 36,000. But really, I want to group these by type, right? So I have a bunch of 2s, right? So I have let's see, 1, 2, 2, 3, 4, 5 2s. So that would be 2 to the 5th, right, that I have as a factor. And then for 3s, I have 1 there and 1 there, so I have a 3 squared. And for 5, I have 3 5, so I'm going to have 5 cubed. So what that tells me then is I can write that 36,000 as 2 to the 5th, I had 5 2s, times 3 squared, right, I had 2 3s, times 5 cubed, because I had 3 5s. This gets me my sort of prime factor decomposition for numbers, right? So if I'm looking at the square root of 36,000, well, that's really looking at the square root of 2 to the 5th times 3 squared times 5 cubed. Now, strictly speaking, I don't need a 2, right? That's why it's not over here. But for upcoming steps, sometimes it's sort of helpful to remind yourself. So you can write the 2. There's nothing wrong with that. You don't have to if you don't need it. I'm going to put it there for what I'm about to do. But optionally, you can always include the 2 if that's sort of helpful for you mnemonically. So now what I want to do, right now we're getting the simplify part. I want to rewrite each of those prime factors as the largest multiple of the root possible in terms of its power, right? So I'm going to do that with one piece, and then I'm going to have a remainder for the other piece. So in particular, if I look at something like 2 to the 5th, I was doing a square root. So the highest power, or the highest sort of number that's a multiple of 2, right, square root 2, the highest that's a multiple of 2 but less than 5 is 4. So I make that 2 to the 4th, right? So that's the highest, 2 to the highest multiple of 2, and then times 2 to the 1, because that's what's left over. For 3 squared, well, that is a multiple of 2, so it's just that, right? The leftover is nothing. There's no remainder. And for 5 cubed, that's going to be 5 squared, and then there's a 5 to the 1 left over, okay? So again, this 2 to the 4th, right, that's 2 squared times 2 squared, and that's why I have 2 to the 4th, is that I'm doing multiples of 2 for my power. All right. So what I'm going to end up doing is I'm going to pull out those sort of groups that I just identified, those things that are the power of the root, but not the remainders. So I'm gonna show this sort of concretely. This is a little hard to describe. But when I pull out each of those things, I'm going to rewrite the term the same way, but I'm going to divide the power by that root value. So in particular, if I'm looking at this thing as 2 to the 4th times 2 to the 1, 3 squared, 5 squared times 5 to the 1, right? These green powers are the multiples of 2, and the red powers are the remainder bits. I'm going to pull out all the green terms, and when I pull them out, they're going to sort of stay the same form. I'm going to have 2 to a power, but I'm going to take that power and divide it by the root power. So I end up with, right, rewriting this as the square root of those green things and the square root of the remainder things. I'm then going to have, right, the 4 divided by 2, the 2 divided by 2, the 2 divided by 2, because that's the original power divided by the root power. And then I can sort of clean this up a little. So if I'm starting with this thing, right, I have the square root that's still there with the remainder. I can't do anything with that. But then I can fix all of those like crazy fraction powers that I'm looking at. And when we get into exponential functions, we'll see sort of a little more cleanly what's really happening here. It has to do with rewriting radicals as powers. But till then, just bear with me here. As a note, though, by design, those green numbers were supposed to be multiples of the purple number, right? You did the largest multiple of the root value. So you did the largest multiple of 2, which means that it should be even. And that means when you divide by 2, you should definitely get whole number powers out here. So as a sort of sanity check, if you have fractional powers on the outside left over, like if you have fractional powers out here, something has gone very wrong. You have made a mistake. Something, you maybe did an arithmetic error, or you pulled out the wrong number to start with, but you definitely should not have fractional powers, okay? But once you've done that, well, now we can simplify all of this stuff by just putting the numbers back together now that we know which numbers are sort of inside the radical versus outside the radical, right? So I can do that 2 squared times 3 to the 1 times 5 to the 1 and get 60 on the outside. And I can do the 2 times 5 on the inside and get 10 on the inside. So the simplified version of the square root of 36,000 is 60 times the square root of 10, okay? Now, square root of 36,000, that's sort of an annoyingly large number, but I sort of wanted to go through all of this in detail with a complicated enough version of this thing so that you can sort of, really see how all of this plays out. It's usually not quite that lengthy, but it's the same process regardless. All right, so that's numeric radicands, but what about algebraic ones? So if I'm looking at, say, this radical here, right? So I have a factored radicand, again, super important, and I'm taking the cube root, and I have all of these things to various powers, right? So the algebraic analog of prime factorization, right, getting all those prime, like 2 to the 5th and 3 to the squared and 5 to the 3rd, the analog of that is a fully factored form. And that's sort of why we need to do that fully factored bit, is that it's the same sort of situation as in the numeric one, only now our factors look weird because they're like x and x minus 1 and x plus 3, right, instead of 2, 5, or 7, and things like that, okay? But it's the same idea. I'm still factoring it. It's just that now my factors have variables in them instead, okay? So once the radicand's factored, that means that we can rewrite the original radical the same sort of way we were doing with the numeric, where we're taking each factor and we're grouping them or splitting them up so that we have the largest multiple of that root again, and then the leftover bits, right? So if I start out with this x to the 5th, x minus 1 squared, x plus 3 to the 4th, x minus 2 to the 8th, I'm going to rewrite each of these terms as the x to some sort of largest multiple of 3, and then whatever's left, right? So the term to the largest multiple of 3. So for the first one, right, and I tried to group these so it's clear where each piece is. So here, x, right, x to the 5th, I can write that as x cubed, right, because 3, multiple of 3, and then I'm going to have an x squared left over, right? So this first part is sort of all of the multiple of 3 pieces that I have, and the second part in the red, that's where all the remainders end up going. So for x plus 3 to the 4th, I can split that up as x plus 3 cubed and x plus 3 to the 1. Again, you don't have to write these, you don't have to write to the first power or whatever in your own work. I'm just trying to make it very clear how this stuff is playing out, okay? So once I've broken it apart into all of these pieces, now I can do, again, the same thing I did with the numeric case. I'm going to pull out factors of that first group, and as I do that, I'm going to divide each power by that root value. So this is where I was a second ago, right, with having split this up with the green part and the red part. But now I'm going to pull out each of these sort of initial factors, leaving them as they are, except I'm going to also divide the power, right? So x cubed, I'm going to divide that cube part, that 3, by the root value, this other 3. So when I do that, I'm going to get x, right, because it's x to the 3 divided by 3, so I'm going to get just x plus 3 to the 3 divided by 3 is x plus 3, and x minus 2 to the 6, so that's 6 divided by 3, that's going to get me a square, so x minus 2 squared, right? So again, same as the numeric part, except now our factors aren't just prime numbers, they're weird looking sort of variable things, but otherwise it's the same thing. All right, so now as a sort of footnote here, if you have numbers involved, right, because we could have numeric parts to a radical, inside the radicand, you could have numeric parts and algebraic parts. I sort of split them up here for pedagogical reasons. But if you had them together, well, now you would do the same thing we did with the numeric part, which is you would sort of put them all back together again for the number part, right? So you would multiply, right? If you had 2 squared times 5 on the outside, you'd do that out. 2 squared is 4 times 5 is 20. You'd write 20 there instead of leaving it in that factored form. But importantly, there's no reason to do this with the algebraic terms. And in fact, most of the time you don't want to do it with the algebraic terms. Like, that would be bad. So as a general rule of thumb, you should only ever expand out those algebraic factors, right? The factors that have, an x in them or whatever, if you have a very specific reason in mind to do that, right? Like, you're thinking to yourself, I need to accomplish this task, right? I need to combine it with this other thing. And so the only way that can happen is if I expand that out and try a thing. So unless you have some very clear, thing that you can say out loud, reason to actually expand it out, don't expand it out. Leave it factored. That's almost always the preferable way, okay? So again, looking at our example, we started out with this sort of cube root of this mess. made it worse, right? So we broke it up into those multiples of 3 and the remainder bits, and then pulled out those multiple of 3 parts. And here, right, if I had a number, like if I had numbers mixed in, I would multiply the numbers back together to make it one number, but I don't. And there's no reason I should be doing that with the algebraic parts. So really, this would be my sort of final form. This would be my sort of completed answer, okay? Now, there is a couple things to sort of mention here. As I tried to make clear, simplifying radicals, it's largely the same whether you're looking at numbers or you're looking at sort of algebraic pieces, right, functions. So it's sort of useful to practice on the numeric ones first because that'll give you a good sort of format for moving to the other parts, okay? So the process, right, first, fully factor the inside. For numbers, you're talking prime factor tree. For the sort of function-y bit or the algebraic parts, you're looking at doing the sort of classic algebraic factoring, like factoring polynomials. Once you've done that, now you can split each factor as that largest multiple of the root and have that as one group, and then whatever the remainder is on the other one, right? You're basically pulling out the equivalent of perfect squares or perfect cubes or whatever. That's really what we're doing here. Step 3, we pull out those factors and do whatever the root is, and the way that works is that we're dividing each of those powers by that root value as we pull it out. So if you're looking at a cube root and you're pulling out an x cubed, it would be x to the 3, right, because x cubed, divided by 3 because it's a cube root. So that's the same sort of process all the way through. And again, true for numbers as it is for algebraic sort of factors. Finally, if you have numbers, you may or may not, if you have numbers sort of involved inside or outside, or both, you want to multiply together the number parts, right, to get one number inside and one number sort of outside at most. Again, you may not have coefficients, so it may not need to do that. But importantly, you definitely don't want to do that with the algebraic factors unless you have some very specific compelling reason to do so. Okay? All right. Now, there is one last footnote here leading to a different video, which we will also be looking at later. But it's worth mentioning here that a lot of information about radicals is going to come up over and over again in different contexts, but a lot of information about radicals tends to sort of be approached in terms of like teaching, learning, tends to be sort of tackled by splitting apart the cases where your radical is even, the radical value, and where the radical value is odd. And there's some very sort of natural reasons to do this, which we'll look at. But important for what we're talking about here, what we did here, it actually was really important that the root value was odd. It was not a mistake that we're using a cube root instead of a square root when we were going through all that algebra stuff. And the reason why is because when we talk about even roots, there's sort of an extra step. And importantly, that extra step is really not obvious on either why it's happening or sort of how to know when to use it or not kind of deal. So it sort of deserves its own sort of video all just for that part of it. And a lot of that has to do with how absolute values and sort of when to use them and when not to. So for what we did here, that is true for all odd roots. And it is the lion's share of what you do with even roots. There's just another extra step that we're going to have another video on. Okay? All right. So what do we do? Well, we talked about radicals, and in particular simplifying radicals, right? We broke it up into these steps, whether it's a numeric radical or whether it's an algebraic radical, right? So the first step is we have to get it sort of decomposed or factored into some sort of idea-wise prime factoring, right? For numbers, they really are prime numbers. In the algebraic sense, these things are sort of variables, right? They're factors in the sense of a factored function, so it's not quite the same as prime, although it sort of is, but that's a whole other conversation with math stuff. You don't need to know that here. But point is that you have to factor whatever it is. If it's a number, prime factor. If it's a function, you factor it like you do with functions, like polynomial factoring. Once you've done that, you break apart each of these factors into basically how much of it is a perfect whatever sort of root version, right? A perfect cube, a perfect square, a perfect fifth degree thing. And you do that by having multiples of whatever that root value is. And then you can pull those out by taking the root, right? Dividing off. And finally, once you've sort of done that, combine numbers together. Don't combine the algebraic stuff together. And that gets you your sort of final simplified form with the asterisk, because always you have that even function issue. You have the even power roots that we sort of need another little bit about, and that's for another video. Okay, so that is that.